Alright, it seems that we're live. Alright, let me get rid of this. Alright, there I am. Everything looks good. So today we're going to learn about error handling in Rust. And this is going to be a lot of fun. Mainly because it's not me doing exercises like the past few times. That was kind of difficult. But in the end, that's why we're learning, right? Is to be able to write Rust, not just read Rust books. We don't do this for the sake of reading. We do this for the sake of learning Rust, right? In order to write it at some point. So I better get used to. Better get used to it. Anyway, yeah. So this is what, part 7 or part 8 of a series of me learning Rust. I should say it's here somewhere. Whatever. It's one of those, and we're going to be learning about error handling, and we've gone through all these other chapters, and like usual, I'm not going to read everything aloud. I'm going to give my thoughts as I read in my head, or I might highlight several things, and I might read aloud some things that I think are important, but in the end I'm not going to read absolutely everything. And it's not going to be me typing out all the example code. I'm not going to be doing that. I'm just probably going to just read it and try to understand from the examples that they give what they're trying to highlight, but I'm not going to be running absolutely everything that happens to be in a coding style. So with that in mind, let's get started. I'll start off by reading all of this just to get us started. So Rust's commitment to reliability extends to error handling. Errors are a fact of life in software, so Rust has a number of features for handling situations in which something goes wrong. In many cases, Rust requires you to acknowledge the possibility of an error and take some action before your code will compile. This requirement makes your program more robust by ensuring that you'll discover errors and handle them appropriately before you've deployed your code to production. Rust groups errors into two major categories: recoverable and unrecoverable errors. For a recoverable error, such as a file not found error, it's reasonable to report the problem to the user and retry the operation. Unrecoverable errors are always symptoms of bugs, like trying to access a location beyond the end of an array. Most languages don't distinguish between these two kinds of errors and instead handle both in the same way, using mechanisms such as exceptions. Rust doesn't have exceptions. Instead, it has the type result template TE for recoverable errors and the panic macro that stops execution when the program encounters an unrecoverable error. This chapter covers calling panic first, and then talks about returning results of TE values. Additionally, we'll explore considerations when deciding whether to try to recover from an error or to stop execution. Alright. So first we're going to learn about unrecoverable errors. And let's see what it has to say. Yeah, so panic, like before it said, is associated with unrecoverable errors, and it just unwinds and cleans up the stack and then quits, along with printing a failure message. Okay, so panic automatically unwinds and cleans up data. It takes a lot of work. The alternative is to immediately abort, which ends the program without cleaning up. The memory that was used will then need to be cleaned up by the operating system. And this is how to specify if you want to use abort style panics. All right. So in your function main, if you just call panic crash and burn, it's going to say thread main panic to crash and burn. It also shows the place where it was called. All right, in this case, it was part of code that we created ourselves, but sometimes it might be in other code. Yeah. And the panic macro is going to be pointing to wherever it was called. It's not going to point to the original function that called it in our own code. All right, now but we could use something called a backtrace in order to figure out who called what that led to the panic. And so let's see how to do backtraces. All right. So we instantiated a vector with 3 elements, and we try to access the 99th or the 100th element, right? Because that, the rest will panic. It panics instead of leading to undefined behavior like C would, because otherwise it would lead to security vulnerabilities. Alright, if we try to run this, it says thread main panic that index out of bounds. The length is 3, but the index is 99. Oh, here it actually did give us where it was panicking. Oh. And the backtrace may include core Rust, standard library code, or the crates that you're using. Alright, so this is how you would run, how you would call cargo run with a backtrace. And so, let's see. So, alright. So first we begin the unwind. So we go from library standard source panicking Rust. So the Rust begin unwind must be a function right in the panicking source file. Then panic, this Rust begin unwind must have been called by panic format, also in panicking Rust, which must have been called by panic bounds check, also caused by Rust. And this panic bounds check must have been called by the index. So the index said, oh, let me check to see if the bounds are okay, and it failed, and so we call a panic bounds check. And yeah, this is some other templating. You know, we go from a template to regular, I guess. I don't know what this is doing, but these are all functions that call it, right? And it starts from main, and then the function all is what I suppose goes into main. I guess release, you wouldn't be able to see these details because they've optimized it out. And this is the actual line that causes the problem in main. Alright, now we'll figure out how to recover from an error. Because panic was used for unrecoverable errors, usually as a result of a bug. Recoverable are pretty much errors that aren't serious enough to require the program to stop entirely. And sometimes when a function fails, it's for a reason that you can easily interpret and respond to. And so in that case, we don't have to terminate the whole program. Alright, so some functions return this result enum either with the OK variant or the error variant. Alright. Yeah, and these are generics. They use generics so that way they can work with a variety of different things. And so now we're going to call a function that returns a result. So here we're going to try to open a file, hello text. I suppose f is going to return the result. Uh-oh. Uh-oh. I don't know what I did there. Anyway. Right, so f is going to be the result type, right? And the result is either going to be a file or error. This corresponds with the OK variant, and this corresponds with the error variant. And this is similar to the sum and none, right? Where if there's something like a nullable value, then it either passes sum or none. And you have to match which one in order to carry on. And in this example, we have to either match to a file, which exists, or to an error, because this function couldn't figure it out, or it failed to open hello text. Right, and so this results enum pretty much tells us whether the function failed or if it succeeded, depending on what sort of what variant it ends up being. And so now we're going to match to, if we get a file, then we what is this, shadow something? I think Rust refers to this as like shadow defining or shadow assigning, because we're assigning f to f, like something from f again. And so you're pretty much allowed to do that. anyway, so yeah, it can either return okay or return an error. Then we match to what it does, and this is sort of the callback of what it's supposed to do. And pretty much if it's okay, it found hello.txt, then f becomes the actual file, whereas before it was just a result type. Now it's going to actually be a file type. Or this f here from the open might just end up being an error, in which case we panic and we print the error. Okay, so we could take different actions depending on what the actual error was. In this case, they want to, for an example, create a file if it doesn't exist, which would cause an error. So if the error is the fact that it doesn't exist, then you simply create it and then you open it. If it fails for any other reason, then we just panic. And so, you have your match statement that we went over, and then for this error, we're going to match to the error kind, or so we're going to figure out what the kind of error is, and if it winds up being a not found, then we match to file create. Remember, this is going to return a result type as well, so we have to match to it to see if it if it's going to succeed or if it's going to fail. And if it's any other error, we also fail. So we fail pretty much if we fail to create it, and or pretty much if it's any other failure than it not being found. Okay, so they're saying that match is sort of verbose. This looks a little ugly, having so many matches inside one another, and so they propose using things called closures to make the code more concise. So, and so these things we sort of encountered while doing the previous exercise, the simple text interface. I suppose this is a closure where we take the error and then we do something with it and then we close it out. And yeah. yeah, so first we open and we unwrap, or else I suppose unwrap is referring to how the stack unwraps if you panic. Oh, no, no, no. Unwrap, oh, what was it? I think I read about unwrap at some point. I forget what it does. Maybe, I don't know. I don't really know. Oh, maybe, okay. Unwrap, what it does is it takes the result type and it tries to unwrap the result and get into the underlying meat of it, if you would, if you will. And that is the actual file handle. But if it can't unwrap, if it ends up being an error, then we take that error and we do something with it. And what do? We do this all the way up to here, I believe. No, we go all the way to here. So this is what we do if we find an error. And we take that error and we figure out, okay, if it's not found kind, and if it is, then you do this, and you pretty much create the hell of that text, and then you unwrap that, or else you take that error and you panic. And if it's not a not found error, then you just panic with the error here. Uh-oh, my bad. My coaster is sticking to my cup, and so when it falls, it makes some noise. Yeah, alright, so yeah, match works well enough, but it can be a bit verbose and doesn't always communicate intent very well. Alright, the result type has many helper methods defined on it to do various tasks, the unwrap or else being one of them. One of those methods, called unwrap, is a shortcut method that is implemented just like the match expression we wrote in listing 9.4. If the result value is the OK variant, unwrap will return the value inside the OK, right? It unwraps the result, right? Like the result is the box, and then you unwrap the box, and then now you have what's in it, which is the actual file handle. But if it doesn't work out like that, if instead you get call, which is an error variant, you call the panic macro, and so unwrap will call it automatically for us. Oh, shoot. Alright. Okay, I guess expect is pretty similar to unwrap, except that you can specify your error message. So bam. And so because it starts with the text we specified, it'll be easier to find the code that this error comes from. And so expect is pretty much a I don't know, a more defined, or I don't know, a more focused version of unwrap. It's not the right word, but you understand. Anyway, when you're writing a function whose implementation calls something that might fail, instead of handling the error within this function, you can return the error to the calling code so that it can decide what to do. Sort of like how file open just punts the error back to us, right? It returns a result that we decide what to do with. It's known as propagating the error. Alright, so here we're defining our own result, which is going to be of a string, or, well, string if it's good, or IO error if it's an error. And so We're going to call this function read username from file. We're going to open hello text. We're going to let mutable f match f. F is trying to open the file. If it's okay, f becomes the file. Otherwise, we return an error of e. We don't panic, we just return it. So that way, whatever calls, we pretty much punt this error to whoever calls read username from file. And then we let mutable s equals string new. And then we match f.read to string mutable s. So I suppose we're just taking all the info from hello text, all the characters, and we're just reading it into this string. And if it works, we return okay, and if it's an error, we just punt that error to whoever called read username from file. So IO error happens to be the same return type as both open, file open, and f.read to string if they're an error. So these could have been different errors, right? They could have been different types. So I wonder how we would have gone about that if they were different. Because, you know, we could have had something that wasn't IO fail, and we may have needed to pass that or punt it along. What's the propagate it? I keep on saying punting. I sort of like punting better than propagating. I think it's, I don't know, more idiomatic? Not idiomatic. I don't know. I like punting. It's more meaty. I don't know. Anyway, I suppose we could have just defined our own error type and say it's an RUFF. It's a rough error type. Read username from file, rough, and then we would have just passed along a struct that said rough days. Anyway, alright, the body of the function starts by calling the file open function. Then we handle the result value return with the match. Right. Yes, this is what I was saying. Right, they don't explicitly say return here because this is pretty much the last expression and that's automatically returned. The pattern of propagating errors is so common in Rust that Rust provides the question mark operator to make this easier. Alright, so how do you do it? Oh, you just stick a question mark right afterward. Awesome. So pretty much you say, alright, let mutable f equals file open hello text, and if that fails, you just pass that error along. I'd like to know if this question mark operator will work even if there are different types of errors. So the error propagated by this or punted by this, ought to be the same type as the error propagated by this, and so that way they can both fit nicely into this type. But what if they don't? I don't know. Okay. So this is going to, oh, but we've put a semicolon here, so that way it's not the last expression. This will end up being the last expression. So this doesn't actually return anything. So like the result of this expression right here, because this is an expression, we don't actually assign the result of this to anything, except we put the question mark operator there in order to pretty much say, if it's an error, then this right here will cause a return from the function instead of simply passing things along. So if this, let's say this expression succeeds, then this question mark says, okay, it succeeded. Let's return this, return whatever, let's pretty much unwrap whatever in it and return. Wait, does it unwrap? I believe it does, because we can just call it here. So question mark should unwrap and put the unwrapped contents into the variable that's assigned to it. This is just we understand this is just a new string, and we're putting it into s variable. And then here we're saying, okay, if we can read everything from the file into this string and it's okay, then we pretty much return this, we return it, but we return it to nothing because nothing is actually assigned to it. But the problem is that, but because it has a semicolon here, the return value is simply ignored, and this is returned instead. However, let's say, part of one of the links of the chain fails. Let's say this ends up being an error. We return from the whole function at that point. Before, when it returned something, even here when it returned an okay, we went along to the next one. Here, if it returns a failure, then it returns from the whole function, and it's the same thing for this. Anyway. Error values that have the question mark operator called on them go through the from function, defined in the from trait in the standard library, which is used to convert errors from one type into another. So that way, let's say this, okay, cool. That's the question that I had before. So, all right, let's read a little more. When the question mark operator calls the from function, the error type received is converted into the error type defined in the return type of the current function, this right here. And so that's how you return that's how you can coerce different types of errors into what you define here. This is useful when a function returns one error type to represent all the ways a function might fail, even if parts might fail for many different reasons. That's what I was complaining about or questioning before. As long as each error type implements the from function to define how to convert itself to the returned error type, The question mark operator takes care of the conversion automatically. Beautiful. Alright, in this context, the question mark at the end of the file open call will return the value inside an OK to the variable f. That's what I was explaining earlier. If the error occurs, the question mark operator will return early out of the whole function and give any error value to the calling code. That's what I was explaining as well. Same thing applies to the question mark at the end of the read to string call. And question mark operator eliminates a lot of boilerplate and makes this function's implementation simpler. We could shorten it by doing this. We chain them together with question mark operators in between them. Man, I'm sorry about that. I'm going to, I gotta be more careful. My stupid coaster keeps on falling. Alright, we're gonna make this even shorter. Oh. We already have the read to string operation already on the file. File string. Standard FS. We pretty much called FS read to string. Oh, this is a good point. The question mark operator can be used in functions that have a return type of result. You can't use it in main, right? Because it doesn't return anything. It doesn't return a result. So main can in fact return a result TE. It's gotta look like this, I guess. But then you're allowed to compile this. So box error, dynamic error, sort of just means any kind of error for now. Alright, so now that we know about recoverable and unrecoverable errors, we're going to learn about the context in which to use them and to panic or not to panic. Oh man. Alright. So how do we decide when we should call panic or when we should return results? If we panic, then there's no way to recover. If we return results, we can recover pretty much. Or at least we give the calling code options. and it can turn a recoverable error into an unrecoverable error if it calls panic, if it finds a result error. And so results are pretty good as a default choice. I said, yeah, I'd say so. So there are situations though when it's more appropriate to call code that panics instead of returning a result. Alright, so example code, you're just, you're trying to get through things. Like in my previous stream, I was handling some errors, right? But the way I was handling them, I was just panicking. I wasn't using any results. I didn't really know how to do a result back then, but that's how I did it, and it helped because I didn't have to waste time on doing error handling when I knew it was just an exercise. And unwrap and expect are very handy when prototyping. Yes, before you're ready to decide how to handle errors, they leave clear markers in your code for when you're ready to make your program more robust. If a method call fails in a test, right, like in a test bench, you want the whole test to fail, even if that method isn't the functionality under test. Because panic is how a test is marked as a failure, calling unwrap or expect is exactly what should happen. Makes sense. These are all sort of in production. No, not in production. As you're developing, this isn't in production code per se. It's just as you're developing, and you need some good placeholders, at least in the actual code. But in the test, you tend to just want it to fail. You just want it to panic, so all right, test stopped. This is where it failed. To fix this. Right, and if we know that we're never going to have an error variant, it's perfectly acceptable to call unwrap, which simply takes the meat out of the result, right? Because we know it's going to pass no matter what, so then we just simply say, all right, we're not going to deal with error handling because we know there's never going to be an error, so we just unwrap it and discard the error checking. Going to clearly separate my coaster from my cup before I start drinking. We'll see how long that lasts. Anyway, we know this is valid, right, as an IP address, so we just parse and then we unwrap the result that parse gives us because we know this is going to return something valid. But the compiler doesn't necessarily know that. Alright, so if the code ends up in a bad state, then it's a bad state and one of them. Okay, if the code is in a bad state and it's not something that you expect to happen occasionally, and the code after this point needs to rely on not being in the bad state, or there's not a good way to encode this information in the types you use, then you just panic. So pretty much errors that you expect to happen ought to be handled with recoverable errors. And if something happens which is totally unexpected and which breaks your code, if it does happen, then you panic. Or at least pretty much if there's a case where you cannot recover from it, then you gotta just say unrecoverable, sorry. When your code performs operations on values, your code should verify the values are valid first and panic if the values are not valid. This is mostly for safety reasons. Attempting to operate on invalid data can expose your code to vulnerabilities. Right, okay, so this is wisdom. Functions often have contracts. Their behavior is only guaranteed if the inputs meet particular requirements. Panicking when the contract is violated makes sense because a contract violation always indicates a caller side bug, and it's not a kind of error you want the calling code to have to explicitly handle. In fact, there's no reasonable way for calling code to recover. The calling programmers need to fix the code. Contracts for a function, especially when a violation will cause a panic, should be explained in the API documentation for that function. Right, at that point, it's sort of it goes beyond the actual function itself and refers to the contract between really the librarian and the consumer of the API, right? It's at that level at which a caller side bug must be, or a violated contract must be handled. And so you don't want to handle it within your code because otherwise it's too much overhead and it's unnecessary so long as the consumer of the API understands what they're doing, right? And so at that point you panic. But this is something that you don't expect ever to happen in final code, right? This is more of the contract. The implicit contract of the function is simply not met, and so you panic for that reason. And Rust is neat in that its type system ensures that we have a variety of things already checked, right? That a lot of boxes have been checked, like types. Yeah, in the case that we decide not to handle option, but instead to handle some other type, then we know, then the contract obviously implies that we're not going to handle a nullable version of this. And so the type checker allows us to make that check automatically in the compiler. Oh, you hear that? That's rain. That's cool. Anyway. Alright, so instead of parsing the guess as a U32, we parse it as an I32, and then we give a hint if it's not within the bounds of what the random number will end up being. In the case of the random number generator guessing game that we created all the way in chapter 2. Okay, but like it's saying here, what if you had many functions that had to have this requirement, that had to have the guess be between 1 and 100? And you can't do that check in every single function. That's just too much overhead. So you have to create your own struct and implementation that checks it before you ever even call these functions. Right, so in the constructor for this guess, you pretty much panic if it's not within those values, and then you do the switcheroo, right? Then at this point we handled it as a hint, and then we continued looping, but here we handled it as a panic, and so the thing terminates. But that way the guess, its functionality, it's already checked whether it's 1 in 100, and the functions don't actually have to check them because it's going to take a guess as its input. And at this point, the conditions in which guess new might panic should be discussed in its public-facing API. Oh, so then whoever consumes this API, right, the programmer who consumes this API, because it's going to be in some library that some programmer is going to download and use as part of his program, he's going to have to do the check outside of this, outside of calling it, or creating a new guess. And so in his code, he's going to check it before we ever get to this panic point. And so this is what they meant by contracts, right? So, yeah. And like I said here, this is something that you specify in the documentation. It's like, hey, look, it's got to be between 1 and 100. Otherwise, you're going to panic and it's not going to work. And so that way, they make sure to put it between 1 and 100. Otherwise, it's going to panic. And so they have to handle it outside of your library, and then everything else is going to work because it's checked upon the creation of guess and not within every other single function that consumes guess. Anyway, that was too long of an explanation for that, but let's move on. Alright, so I'll just read aloud the summary. Rust's error handling features are designed to help you write more robust code. The panic macro signals that your program is in a state it can't handle and lets you tell the process to stop instead of trying to proceed with invalid or incorrect values. The result enum uses Rust's type system to indicate that operations might fail in a way that your code could recover from. You can use result to tell code that calls your code that it needs to handle potential success or failure as well. Using panic and result in the appropriate situations will make your code more reliable in the face of inevitable problems. Now that you've seen useful ways that the standard library uses generics with the option and result enums, we'll talk about how generics work and how you can use them in your code. Alright, so, oh no, if the look at this is the intro to generic, and it's in itself a huge page. Let's look at this. Oh man. All right, so we only have really an hour left of learning, so I'm going to. I definitely want to use this hour to do this, to look at this, but I don't think we're gonna get through it. Yeah, there's no way we're gonna get through this. Yeah, I don't know. I might just call it quits then for this stream. And then we can devote 2 hours next stream for going through all this. Unless there's a smaller topic later. Not really. Let's go to macros. Alright, we're going to learn about macros instead of generic types. I feel like we've been using macros, right? We should probably learn about them. And then, this is an advanced feature, but I don't know. Maybe it'll be too much. Let's see. This part of the appendix? No, it's advanced features. Oh, here. Okay, the difference between macros and functions. Fundamentally, macros are a way of writing code that writes other code, which is known as metaprogramming. All right, let's just read the introduction. We may instead read Appendix C about derivable traits because it says here that we sort of need this. It sort of introduces it or mentions it to us. So let's just sort of introduce macros, and then when derivable traits become too insistently used in this article, then we'll look at derivable traits instead. So we've used macros like print line throughout this book, but we haven't fully explored what a macro is and how it works. The term macro refers to a family of features in Rust: declarative macros with macro rules and 3 kinds of procedural macros. And these are custom derive macros that specify code added with the derive attribute used on structs and enums. Attribute-like macros that define custom attributes usable on any item. And function-like macros that look like function calls but operate on the token specified as their argument. Oh. But operate on the token specified as their argument. Huh. Really? Huh. Because when we use the print line macro, we can define a variable which value actually gets used within the string that we're printing. So it's strange that function-like macros that look like functions, but they only operate on the tokens that are specified. So it only operates on the X token. I guess it doesn't treat X as a variable, but it ends up referring to the content of that variable. Alright, fundamentally, macros are a way of writing code that writes other code, which is known as metaprogramming. In Appendix C, we discussed the derive attribute, which generates an implementation of various traits for you. We've also used the print line and vector macros throughout the book. All of these macros expand to produce more code than the code you've written manually. Metaprogramming is useful for reducing the amount of code you have to write and maintain, which is also one of the roles of functions. However, macros have some additional powers that functions do not. A function signature must declare the number and type of parameters that the function has. Macros, on the other hand, can take a variable number of parameters. We can call println hello with one argument or println hello name with two arguments. I didn't know that functions can only have a definite number of parameters, because there are other languages that can have however many parameters you want, or you can expand the list of parameters. That a function can have. Alright, also macros are expanded before the compiler interprets the meaning of the code. So a macro can, for example, implement a trait on a given type. A function cannot, because it gets called at runtime and a trait needs to be implemented at compile time. The downside to implementing a macro instead of a function is that macro definitions are more complex than function definitions because you're writing Rust code that writes Rust code. Due to this indirection, macro definitions are generally more difficult to read, understand, and maintain than function definitions. Another important difference between macros and functions is that you must define macros or bring them into scope before you call them in a file. As opposed to functions, you can define anywhere and call anywhere. So, it mentioned derive. So we're going to learn about declarative macros first, with macro rules for general metaprogramming, and it's supposed to be something similar to a Rust match expression, but obviously it's going to be different. It's going to be probably more powerful given the definition we had before here. And for an overview of match, it says match expressions are control structures that take an expression, compare the resulting value of the expression to patterns, and then run the code associated with the matching pattern. Macros also compare a value to patterns that are associated with particular code. So it takes a value and it compares it to patterns that are associated with particular code. In this situation, the value is the literal Rust code, Rust source code passed to the macro. So what we're going to be comparing to patterns that we define in the macro is itself literal Rust code. So the patterns are compared with the structure of that source code, and this code associated with each pattern, when matched, replaces the code passed to the macro, and that all of this happens during compilation. So, okay, that's cool. So you call the macro with some source code, the literal tokens of the source code that you have. You pass it in, the macro takes that source code, it compares it to a variety of different options, right? It compares it to these different patterns, and depending on what the source code that you passed in looks like, it's going to choose one of these callbacks, let's say, that is associated with that pattern. It's going to take that source code that's associated with the pattern, and it's going to replace that source code that you called the macro upon in the actual file itself. So that's cool. So, oh, look at that. Look at that. Beautiful. Beautiful stuff. That's what it's talking about as being a little harder to understand. And it looks like, you know, regular expressions, you know, just always fun. Anyway, so we just define a vector. Well, I suppose we're just going to look at how the vector macro is defined. So we could use, the vector macro is defined. So we can use this macro to make a vector of 2 integers or a vector of 5 string slices. We wouldn't be able to use a function to do the same because we wouldn't know the number or type of values up front. And this is sort of a simple definition of it. Yeah, so the actual definition is more complicated, but here's just a simple version of it. So this is going to be the definition of the Vec Macro right here. And what it is I suppose we match this to this, and I have no idea what it's doing. So obviously we're creating a new mutable vector, and so inside maybe the first the first parentheses, inside these parentheses, this is the whole thing, and then it's going to have 2, and I suppose it's going to have this separated by an arbitrary amount of commas. So this can be, I suppose, replicated over however many times you'd like. And within this is this. And we pretty much match this first thing here to this, right? So these first set of $ parentheses is matched here, and the whole thing is matched here. And so you're taking the contents of this and you're doing something with it here. And really what you're doing is you're taking this temporary vector and you're pushing the value of x. So this is another thing that we're going to be taking. And I suppose x is just some expression. And remember, an expression is 1 can be an expression, 2 can be an expression. Something that just returns something is an expression. So pretty much we take whatever this is and then we push it. And I suppose I'm not sure what this, I suppose we do this an arbitrary amount of times is what this is saying. And the pattern, maybe this is the pattern, and then it's simply this pattern however many times. And it's, when it happens, for every single one of them, you do this, you know, however many times this pattern shows up, and then you just return the vector. That's my understanding of it, just by looking at it and guessing. Let's see if my intuition is correct. Here we have one arm with the pattern. So it's right, it's just only one arm. It's this. This is the pattern, and it's followed by this, and we define the callback for this pattern, which is this. This is the whole callback, and so at the end of it, we just return this. Now, I'm not sure why we have intermediate block inside of an already present block, but I don't know. And the block of code associated with this pattern. If the pattern matches, the associated block of code will be emitted. Given that this is the only pattern this macro, there is only one valid way to match. Any other pattern will result in an error. More complex macros will have more than one arm. Valid pattern syntax in macro definitions is different than the pattern syntax covered in Chapter 18 because we don't know what that is. Alright, so now we're going to walk through what this pattern actually means. Alright, so first, a set of parentheses encompasses the whole pattern. That's what I figured. A dollar sign is next, followed by a set of parentheses that captures values that match the pattern within the parentheses. A dollar sign is next, followed by a set of parentheses that captures values that match the pattern within the parentheses. Okay, so parentheses now defines a new sub-pattern that we're going to match to. That's what it's saying. For use in the replacement code. Within dollar sign of that is dollar expression, which matches any Rust expression and gives the expression the name of X. The comma following dollar indicates that a literal comma separator character could optionally appear after the code that matches the code in here. So this, is it optional it said? I wonder why the comma is optional. Is it because it's, no, it's not because of the star. The star simply says that everything preceding it could happen either 0 or more times, because we could in fact instantiate an empty vector, right? I wonder why this is optional. I don't know. Anyway. When we call this macro with vec 1, 2, 3, the $x pattern matches 3 times with the 3 expressions 1, 2, and 3. I'm not quite sure what dollar does. So it's still a little fuzzy for me, but now let's look at the pattern in the body of the code associated with this arm. Temp vec.push within dollar blah star is, okay, so temp vec.push within this block is generated for each part that matches this in the pattern 0 or more times, depending on how many times the pattern matches. So that's what I figured. So this right here corresponds to this. And so for each one of these, which could be 0 or more times, indicated by this star, you do this. And so that's why you have a dollar sign, because you need to first match the outside of it, and then within that, you have a particular expression that you want to store into X. And this X is what you replace here. Okay. And so this code, and that's why you want to put it all into its own set of, into its own block, because macro is just going to replace the source code, and you don't want this temp vec to be available outside of the scope of the macro, and so you have to replace it all within its own block so that this gets out of scoped later, but this gets returned from the block, like here. Okay, so macro rule is going to be deprecated soon because of some strange edge cases, so we're not going to worry ourselves too much about it. Alright, the second form of macros is procedural macros, which act more like functions and are a type of procedure. Whereas the previous one was more like just replace it like a match expression or match patterns and then replace. This is going to be more like a procedural macro, which acts more like a function. So procedural macros accept some code as an input, operate on that code, and produce some code as an output rather than matching against patterns and replacing the code with other code as declarative macros do. The three kinds of procedural macros, custom derive, attribute like, and function like, all work in a similar fashion. When creating procedural macros, the definitions must reside in their own crate with a special crate type. This is for complex technical reasons that we hope to eliminate in the future. Using procedural macros looks like the code here, where some attribute is a placeholder for a specific macro. So use procedural macro, and then you have some attribute, public function, some name. So it's pretty much, this is an example of using a procedural macro, where this is a placeholder for some other macro. And so I suppose you use this macro upon this function. Or maybe public function, some name has nothing to do with some attribute. I'm not sure. Anyway, the function that defines a procedural macro takes a token stream as an input and produces a token stream as an output. Oh no, this is the definition of this attribute or this macro. Okay. The token stream type is defined by the proc macro crate that is included with Rust and represents. Now I'm confused. So the function that defines a procedural macro takes a token stream as an input and produces a token stream as an output. Alright, so it's saying that the function that defines a procedural macro, and it seems that that's what this function is doing. The token stream type is defined by the procedural macro crate that is included with Rust and represents a sequence of tokens. This is the core of the macro. The source code that the macro is operating on makes up the input. Okay, the source code that the macro is operating on makes up the input token stream. And the code the macro produces is the output token stream. The function also has an attribute attached to it that specifies which kind of procedural macro we're creating. We can have multiple kinds of procedural macros in the same crate. Look at the different kinds of procedural macros. We'll start with a custom derived macro and then explain the small dissimilarities that make the other forms different. Alright, so now we're going to do a hello macro that defines a trait named hello macro with one associated function named hello macro. Rather than making our trait users implement the hello macro trait for each of their types, we'll provide a procedural macro so users can annotate their type with hash derive hello macro to get a default implementation of the hello macro function. The default implementation will print hello macro, my name is type name, where type name is the name of the type on which this trait has been defined. Alright. This is getting over my head. I don't even know what a trait is. And so we'll create, so in other words, we'll write a crate that enables another program to write code like this using our crate. So I've never seen this before, where we derive hello macro as, and then I guess for the pancake structure. So I'm going to put my expedition into macros on a hiatus at this point because I'm not sure what this is doing, because it is a custom derive macro. We don't even know what derive is. It's like here. Alright, so I managed to gain about half an hour out of at least these declarative macros. So I think that's good enough for now. I think it's pretty much time to call this the end of the stream because I don't know what this is, right? I'm not sure what this is doing. I've never used something like that. And I could try to look at derivable traits, but I don't even know what a trait is. And where are we going to learn about traits? Oh, we were just about to learn about them. Oh, beautiful. Beautiful. All right, so that's a perfect segue, isn't it? Okay, next time we'll learn about traits that are sort of necessary in order to learn about a great variety of macros that we ended up skipping learning traits in order to learn about. So, you know, that that tends to be how it goes, isn't it? Anyway, I'm gonna call it now. All right, I hope you guys enjoyed this. Even though the later half of it was a little expeditionary in nature, because we couldn't really get into generic types. That would have been too long. I would have had to split up the stream into two, and I wouldn't want to do that, especially if it seems like I could do this all in one stream. It would be 2 hour stream for just one chapter, but I think it'd just be one stream. And if not, then surely I will regret not spending some time now and learning, or at least pursuing it. Anyway, I'm done. So let's call it an end. I hope you enjoyed it. I suppose until next time, guys. Peace.